Okay, now let's think about the second class of applications of Gauss's law. So this is Applications of Gauss's Law, Part 2. Which is about the electric field in and around metals. So in a metal, you have many mobile electrons. You've got from 1 to 3 mobile electrons per atom. So that's a very large density of electrons that can move around very freely. And sometimes this is called a sea of mobile electrons. However, overall, the metal is electrically neutral. So one way to picture it is you've got fixed nuclei with some electrons that are fixed around them. And then surrounding this, there's kind of this sea of mobile electrons. But the whole thing is electrically neutral because you still have the same total number of protons and electrons, electrically neutral. Okay, so what's the consequence of this? Let's take a piece of metal. I think I'm going to make this metal purple. So this is a block of metal. We're seeing it in cross-section here. And I'm going to apply an external electric field. And again, don't worry about where this electric field is coming from. But let's just think about what is its effect on the metal. So this is a uniform electric field which is pointing to the right everywhere. So that electric field is going to exert a force on the electrons which pushes them to the left. And they're very mobile, so they're going to go as far to the left as they can get, and so you're going to get a buildup of a negative surface charge density on the left-hand side. As you are pushing the electrons to the left, there's a tiny little bit of area here where you push the electrons away from it, and so you're left behind with a positive surface charge on the right. Again, the block of metal is electrically neutral, so there has to be the same density of surface charge that's positive on the right side and surface charge that's negative on the left side. As you're pushing the electrons so that they're moving, essentially you're moving them from this side to that side. If we think about the electric field just due to these two surface charges, the electric field due to this positive surface charge would point away from it. The electric field due to this negative surface charge would point towards it. We can model these as infinite surfaces. They're not actually infinite, but they're surfaces, and we know, at least in terms of the direction, that both of them would create an electric field that points to the left. Notice that that electric field, due to the charges in the metal, is pointing opposite to the applied electric field. The longer we apply the electric field, the more these surface charges build up, and eventually they're going to build up to the point where this field, due to these surface charges, cancels out that external electric field, so that the total electric field inside of this is 0. So at that point, I could use our other way of drawing the strength of the electric field, that is where the length of the vector indicates the strength of the field. So here is the externally applied field, and here is the electric field due to the surface charges. I'm including both surface charges, so E sub surf for surface charges. And the electrons are going to keep on moving until these two have equal and opposite magnitudes, and so the total electric field inside the metal at this point is 0. If the total electric field were not 0, let's say if E surf were a little bit smaller than E ext, then you would keep on pushing electrons further to the left and building up more surface charges, which makes E surface bigger, until you got to the point where the total electric field is 0. So this is a quite important finding, that the total electric field inside a metal in equilibrium, meaning that there is no net motion of the electrons, is 0. So that's a 2-star box. Now actually establishing this equilibrium occurs very quickly. So this occurs in less than 10 to the minus 12 seconds. So very, very quickly from the time where I put on the external field, the charges within the metal rearrange themselves so that the total electric field within the metal is 0.